So we have 1 hour and a half for the 4 presentations plus Q&A sessions. Q&A will take place at the end. It's better if we have a time for the questions. And so I give the floor to Dr. Robert Barthorpe, please.
Okay, thank you everyone. I'm setting myself a timer because I have a terrible habit of overrunning. I've given myself 10 slides, but I could talk all day about them if I chose to, if you'd allow me to. So yes, thank you for the introduction. I'm Rob Barthorpe. I'm a senior lecturer at the University of Sheffield in our new, as of this month, School of Mechanical, Aerospace and Civil Engineering. We've brought a few departments together, but I'm from a mechanical background, but work closely with our civil engineers. The project I'm going to talk about today is called Advanced Distributed Storage for Grid Benefit, or ADSorB for short. And I'll talk about the partners, the background, what we're trying to achieve, and show you no results and no technical outcomes. But if you'd like those, please come and talk to me because we're getting some very interesting data coming off the project. And I'll finish with some pleas for coming and working with us on future projects and kind of looking at the way forward. We're very open to what comes next. The motivation for the project itself, I think I'm sort of preaching to the converted on this. We need to do something about the future energy grid and how it's going to operate as we move towards intermittent renewables as being our main source of supply, and as we adapt to changes on the demand side as well, as we electrify heating, electrify transport, electrify large parts of industry as well. There's all sorts of decarbonisation going on. Electricity is the future. But in order to address this supply-demand imbalance, whether it's over a day or over seasons or everything in between, we're going to need to build flexibility in at all stages in the process. So different storage options or different demand response solutions that we can bring in at different stages. Our particular focus is looking at what we can do locally, so particularly within buildings or potentially on heating networks, so that we've got energy stored at point of use. You can see all sorts of co-benefits to doing so in terms of what we can do to alleviate local grid constraints, solve some of the problems for the distribution companies when it comes to decarbonising portfolios of properties that are all fed by a single feeder, for example. But also the co-benefits that come from energy stored at point of use, being able to draw that down during off-peak periods, the benefit for the end user in having the certainty of knowing that they've got energy, whether that's electrical or thermal, at the point of use. Our particular focus is on thermal energy solutions. So we think electrical is going to play some part in the mix, but equipping 28 million homes in the UK, for example, with large lithium-ion batteries probably isn't the best use of resource. So we can see electrical being a smaller part of the mix. Thermal energy offers lots of benefits in terms of durability. We're designing systems that will last for 25 years plus, cost, the materials that are used in building those devices. And I'll talk about the materials a little as we're going through. So our particular approach within the project is we're trying to take two more advanced thermal storage technologies suited to domestic dwellings from TRL 4 or 5, where they are at the moment, or they were at the start of the project, through to TRL 7 and doing demonstration in practice. So we've got the thermal storage solutions themselves and how we're developing them, but also looking at the interoperability and the control systems that we need to make them work as part of a low-carbon system within a home. And the overall idea is that implemented at scale, these kind of technologies can make a major contribution to a phrase such as UK energy flexibility, because it's a UK project, but European flexibility, global flexibility, if we're able to bring them in. The funding itself is provided by the UK government through the Department of Energy Security and Net Zero under the Net Zero Innovation Portfolio Longer Duration Energy Storage Challenge, which is a bit of a word salad. But the focus was on trying to develop new extended duration storage devices. And that was phrased as being 4 hours plus. Essentially, it was trying to look at solutions beyond lots of lithium-ion batteries in fields as being the solution to UK energy storage. So we're looking at solutions that either work within the day or potentially across several weeks or even months for the thermochemical solutions we're looking at. We had a first short feasibility stage in 2022, followed by the current implementation stage that's due to run until January next year. So we've got a heating season ahead of us to get most of our data. We've got 4 project partners. So Loughborough University essentially are the technology providers in a sense, in that they've looked at the thermal storage technologies on both sides, demonstrated them in the lab at different scales, and that was the starting point for the project. And during this project, they're doing the prototyping, the onward design, the manufacture for the trial sites. I'm from the University of Sheffield, where we're leading the project overall, but we're also focusing on the laboratory-based characterization of both the stores themselves and their operation within a lab-based system, doing performance optimization work, leading on the control side, particularly model predictive control software, and looking at state of charge estimation, which is a challenging problem, particularly for PCM storage solutions. The University of Nottingham are looking after the field demonstration. I'll talk about the fantastic test bed they have down there in Nottingham. And then we're working with Mixergy as our commercial partner. They already offer a grid-connected stratified hot water solution that's kind of at the cutting edge of hot water technologies. But they've been looking at the control hardware and bringing all their expertise on product development and routes to market and commercialization as well. A brief talk about the 2 technologies themselves. The first is based on phase change materials, which may be familiar to some. So the classic thermal storage solution is you heat up and cool down some hot water or some other medium, and it gets hotter and colder. Phase change materials make use of latent heat storage, so we're melting and resolidifying some active material in order to store heat in a much denser form. So the rule of thumb that often gets used is around an energy storage, energy density increase of about 3 to 1 from a hot water tank to these kind of phase change material stores. So you get a lot more heat into a smaller space. And there's some control over the form factors. Cuboidal storers we're looking at there will often fit into a property a lot more easily than a hot water storage tank. It's the kind of solution that you could fit under a kitchen cupboard or in a storeroom without losing a great deal of space. And you get some other co-benefits from the PCM storage as well. The particular material we've chosen is commercially available. It's provided by Crowdertherm. It's got a phase change temperature of 53 degrees. So when we're discharging these stores, we get heat coming out at around just below that phase change temperature, which works really well for domestic applications. We've designed the system so that they work with heat pumps for charging and then discharge to the home. And again, 53 degrees gives us a nice medium where we've got a little bit of overhead, where a modern heat pump can charge that with a 10 to 15 degree delta. But it also gives us some overhead above the 40 or 45 degrees that's really useful in properties. So we've been developing these as modules, essentially, where we can run various of these stores kind of alongside each other, either in series or in parallel. And each of those stores that we see there holds around 4.5 kilowatt hours of heat, so roughly a bathtub's worth. So a useful contribution. So that's one set of storage devices. The other, the one that was coming probably from a lower TRL level at the start of the project, is based on thermochemical storage. So here we're, rather than melting and resolidifying, we're essentially looking at drying off the active material when we've got energy available to us during the charging process, so drying things out. And then when we rehydrate that active material, we get a great deal of heat in response. So we can dry things out and rehydrate them. The real benefit of these storage solutions, as well as even greater energy densification, is that effectively we have no standing losses. Once you've dried off these materials, as long as you can keep them dry, that thermochemical potential is maintained for as long as you want it to. And that could be days, that could be weeks, that could be interseasonal if you really, really wanted to. In effect, you want to do some cycling, otherwise you never get any return on investment. But could be very well suited to overcoming wind droughts, for example, where having storage over a few days or a couple of weeks could be a very useful solution to you. We are deploying these into homes, and you might look at that system that sat in the lab and go, I wouldn't want anything like that on the side of my house. This is a prototype. This is generation 1. We have a Gen 2 store that's roughly half the height, and the planning for Gen 3, which is a much lighter weight vessel made of aluminium with stiffening elements, etc. So there's a pathway towards this being something that could be deployed in homes. In truth, we see this as being probably better suited to district heating networks or to hospitals, other large users, where the aesthetics and the spaces may be less of a constraint and outweighed by the benefits of the solutions. So the work that we're doing, particularly in Sheffield, is around the characterization and state of charge estimation development work. So what we're able to do is take these individual storage devices and put them in well-controlled environments. So the image at the top there is our laboratory for verification and validation that's got a sequence of environmental test chambers. So we're able to set things up such that we've got the stores within the environmental chambers. We can then simulate the environment, both heat and humidity around that, and do some very high quality testing on the units themselves. Through that, we're able to characterize the round-trip efficiency of these units over different standing durations. So we've got some really nice round-trip efficiency curves over different storage durations, demonstrating these units, the PCM units, can themselves offer storage over several days usefully. Like I say, in practice, you'd probably use them intraday, you'd be charging during the night or during pre-peak periods, and then drawing the heat down during the peak periods, which are typically between 5 and 10 of an evening. With that characterization work as well, obviously we get a good idea of the charging and discharging profiles that are available to us. It enables us to look at different discharge formats. Do you try and get everything out at once, or do you try and maintain a given output temperature for a period of time by mediating the flow rate? And it gives us a fantastic set of data for our state of charge work. Big challenge with PCM stores is if you pepper them with temperature sensors internally and then wait and see what happens during the latent phase, you just see a lot of 53 degrees. It's not very informative to use temperature sensing to try and estimate the state of charge of these units. So we're looking at different ways of using temperature sensors and different temperature modalities, lots of system identification work to be able to say what's actually happening within these units, particularly during these standing periods. All of that's based around the PCM work. The TCS stores, the thermochemical storage devices, were being installed in the lab yesterday. So it was a bit nerve-wracking being over here while things were happening in the LVB. But we'll be doing an analogous set of tests with those thermochemical stores in more demanding conditions, because these may well be stored outside, to understand the discharging and charging profiles we get to see. As well as doing that module level characterization, these sort of gold standard tests, if you like, on what the stores themselves do, we're looking at seeing how they operate within built systems. So this is a step towards the real world, which I'll talk about on the next slide, where we've built, a couple of slides time, where we've built a system level demonstrator in a laboratory in Sheffield, but that's got all the characteristics of a real home and actually replicates the systems in our trial homes down in Nottingham. So maybe a little bit small, but that top image there, we can hopefully see we've got a blown air space heating system on the top there with various modes of operation where we can heat the lab space or just pass waste heat out to the outside, or when we're being particularly green, heat up the broader building by discharging through this vent here above the doorway. We've got a space heating system with variable loads. We've got domestic hot water drawers as well. And then we've got a very flexible set of operational modes that we can achieve through this very large amount of copper on the back wall there. So there's lots of different ways we can use thermal storage within homes. The simplest, the classic way, is you store it up and use it for hot water. We're also using it to service the space heating unit. And then you get the more interesting modes of operation where you might use the stores to preheat the return flow to a heat pump such that you're taking a load off the pump during the peak times. And that can be a really good way of using low-grade heat in particular. As you're starting to empty your store, you're maybe not getting the return temperatures you really want to. You can still make use of that by preheating flow to the heat pump. So we've set things up such that we can do all of those modes of operation, and we've got a heat pump in the system as the generator for the time being. This also means that we can look at the control side in depth. We can trial different predictive control options. We can demonstrate the interoperability of the different systems, both that we're designing and with other low-carbon things like the heat pump itself. Ultimately, it means we can trial things before we roll them out in the real world. It also gives us the data that we need for our model predictive control work. So essentially, we're looking at dynamic scheduling and how you might be able to make use of forecasts of upcoming demands, weather, time of use tariffs, any of the flexibility services, and do ongoing optimization on that basis to work out how best to operate the system. So we've built our own sort of dynamic scheduling tools based on MPC and based on forecasting and demand estimation work that we've been doing ourselves, and that's implemented through the Mixergy hardware. The idea here being that ultimately we want control to be simple for the end user and for the installer. The ideal control system at a home level would be predictive and grid aware. It should essentially be delivering heat to the user at the best value possible, but without requiring their interaction. So we've set things up such that the end user can run their system just as they would do, set their heating schedules when they want their home to be warm or to be cool, learn about their hot water usage, for example, and then let the system sit in the background and just deliver that heat as they want it to maintain their comfort at the lowest cost available. Obviously, there are extensions of that where you might want to weight cost and carbon usage, because we have ways of getting hold of the grid carbon intensity, for example, within the UK, and we can make that part of the balance for those who are particularly eco-conscious, because those things don't always neatly tie up. So we built tools for doing that, and they are working, demonstrating in the laboratory before trialling them in the homes. If I move on to the homes themselves, this is kind of the really key piece of the program in terms of generating the critical research outcomes, doing the learnings about what happens when we've got humans in the loop, essentially, so that we can better inform the next stages for the program. And it's obviously of great value to our funder, who want to learn how these things actually work in practice. They like lab data, but real-world data is worth so much more to them. So the in-home demonstrations are happening down at the University of Nottingham. They are very fortunate. They have this campus of 7 properties on their site, most of them being homes, some of them being office spaces, but all built to different standards. They're also served by a small district heating network. So they've got a prosumer-consumer network with a 10,000-litre water store at one end of this street of properties, and we're deploying the TCS unit onto that district heat network as well. So the 2 properties we're dealing with, there's a 1930s semi-detached property, which is very, very typical in the UK. There are thousands of these out there. They built one to 1930 standards and retrofit it as part of a previous program. So it's a fantastic test bed for us to be able to go in and show what you could do in that kind of retrofitted property that is so typical for us. We also have a newer build construction, something built to code for standards based on the future home standards in the UK. So this is an example of a new build, essentially, a much better insulated property, so we can demonstrate how things work in there. So as we stand at the moment, we have the PCM stores installed in these properties. We're getting data on how these things work. That's always incredibly informative, because once you step away from the laboratory and you learn about the constraints of charging with a heat pump to a PCM, for example, and the restrictions that places on your system, we learn a great deal from that. The basics of just the plumbing and whether you set this up as being an addition to a primary circuit or on a secondary circuit and so on. So we've learned a huge amount just by seeing how these things work when they meet reality. And we have the thermochemical stores on site being commissioned this week, so we'll be getting data from those in the very near future as well. So that's where we are at the moment. I say we're running through till the end of January, so we're just getting to the stage where all the hard miles are hopefully done, and the data starts rolling in, and we very rapidly start bringing things together and communicating them. So watch this space. I'd end with the slide of, well, what next and how does it impact those in the room and beyond? Really, we're looking to what comes next and looking for possibilities to work with people into the future. So in terms of the capabilities that we've built up through the program and beyond, we've got this existing multidisciplinary partnership with an SME on board and with a set of academic partners that work very well together. We've got the storage technologies themselves, which may be of interest and say should be heading towards TRL7 by the end of the program. We've got a whole suite of facilities for characterizing things in the lab or in controlled environments at system level through that new lab that's being developed. And we're also looking towards building another community energy demonstrator in Sheffield over the next 18 months or so that will give us more capability in this sort of test arena. We've got the SME partnership with Mixergy. We're also very closely involved with some of the other novel thermal storage technology companies that we have in the UK. We have a small set of very interesting companies looking at different kinds of thermal storage suited to properties and heat networks. And of course, we've got the modelling, optimisation and control work that we're doing in Sheffield itself. In terms of who we might be looking to work with, there's the set of people you might expect. So trial hosts, municipalities, etc. People interested in scaling things up on the manufacturing side, because this will be key to turning this into a commercial proposition. Can we actually scale this up in a sensible way? Working with DNOs or energy service providers to explore the tariffs and flexibility services that might feed into making these things a success. And also learning on the social side, what are the barriers to adoption for consumers, and can we overcome them? Can we overcome lack of familiarity with technology? Can we make people more aware of the tariffs and how they might be used to make these kind of systems beneficial to them? Okay, I will end there with questions. I know we're going to do most of them at the end, and I'm really pleased I'm only 30 seconds over.
So thank you very much, Robert. Probably we will go through all these presentations and the questions we will ask to you at the end of all these four presentations.
Absolutely.
Thank you very much for the interest.
Thanks.
So, the second presentation will be done by Beril Alpagut from Demir Enerji to present us Propel project. So, the floor is yours.
Thank you. Hi everyone, this is Beril from Demir Enerji. Today, actually, this paper and presentation was developed by Hande Demirel, a professor from Istanbul Technical University working in the geometric engineering faculty. She couldn't make it to the conference, so I'm conducting her presentation. I hope, I'll make it as she likes. So it's about exploring the sustainable energy potential in positive energy districts and via GIS systems. So what is a positive energy district? As most of you may know, it's a concept evolved from the carbon neutral and zero energy communities, and it's for reducing energy consumption and increasing renewable energy production in line with the UN's Sustainable Development Goals. So the energy generation, the on-site energy generation, should be higher than the energy consumption, final energy consumption, and the surplus of energy should be shared with the neighboring with the grids. The positive energy districts, they are designed to produce net zero emissions and be self-sufficient in energy. This is the explanation, the definition for the Propel project, actually. And within these zones, renewable energy technologies and integrated energy systems are used to meet the citizens' basic needs, including, for now, electricity, heating and cooling, and also domestic hot water, actually, with an annual surplus of renewable energy, as I explained before. What could be the challenges of developing positive energy districts? The first challenge is the decision-making for planning and managing and operating such systems, because they are very complex systems. So it requires tailored frameworks, models, and tools, innovative tools, I may say. And there is also still discussions on how to identify PET boundaries, actually. So it should be feasible. PET boundaries, the definition of it, and potential use of sustainable resources within the area, or also outside the boundary could also be possible. but it's still under discussion, as I said. And also there are lots of criteria for PET developments. Lots of different criteria could be for PET developments, but their importance needs to be assessed from context to context, from geography to geography. So this is also one of the other challenges. And what could be the opportunities? Actually, I will here just mention about the digitalization part. So the GIS systems, the spatial information science could work well with the PET developments at design stage, at planning stage, and also at the implementation operation stage as well. Artificial intelligence, including machine learning and deep learning, mainly on the design and again in the operation stages. So the digitalization of PETs, digital twins and visualization of PETs could be the opportunities for PET developments. You see some of the, Horizon and other smart city and city mission projects here about positive energy districts, and there is also this JPI Urban Europe Development DUT calls for not for implementation projects, but mainly on the planning and design of positive energy districts. And Propel is one of the projects funded under DUT, the JPI Urban Europe funded project. And its aim is to expand the positive energy district energy system with biogas, focusing on biogas and transportation mainly. And there are 3 countries involved in the project: Sweden, Italy, and Turkey. And there are 5-6 pilot sites in these countries. And today, in this presentation, I will focus on the Kadıköy, Istanbul pilot in the project. And in the Kadıköy province, several different sustainable energy sources need to be examined for the beginning of the project. And after assessment of the resources actually available in the district, in the city, Caferaz district was chosen for understanding the energy generation potential of solar energy generation potential actually, and solar energy potential was examined within the scope of the study. And seasonal differences were examined with sun-hour analysis and the shadow change during the day, and the sun-hour studies during the day were also examined. So this research is focusing on the solar energy generation, okay? But of course, for PET generations, other resources, available resources should be examined, and also the energy consumption should be examined as well. So the methodology for assessing the solar energy generation is consisting of 3 steps. The first step is the data acquisition, building data including the number of stories, the construction year, and also the building uses, I think, were gathered, collected to generate the 3D models, the 3D building models. And then the analyses were performed for sun hours, shadow change, and solar energy potential. So you see the 3D model of the Caferaz district that I mentioned. The analyzers utilized building data from the study area, which contains details such as construction year and the number of floors and building uses of the buildings. And all this data was considered to generate the 3D model of the study area. So regarding the analysis, so as you see, the analyses were conducted at different times of the period of the year. So this is from May, and you see 60% of the study area is exposed to sun more than 9 hours. For example, in October, in autumn, and 49% of the study area is exposed to sun for over 9 hours. And you see 3 different hour, again, the shade analysis. So at noon, there is less shade compared to the morning and afternoon, and buildings are more exposed to the sun, with shade prevalent towards sunrise and sunset, and more shade at sunset than at sunrise. And regarding the solar energy potential of the district, the annual energy potential of the study area was conducted, and it was around 630 million kilowatt-hour per year, and also it's also analyzed for square meter as well in average. So as concluding, within the scope of this study, as I mentioned, sun hours and solar energy analyses were performed to evaluate the solar energy potential of the Jafra district. And the shadow conditions during the day were examined as well. To examine the seasonal differences, also different times of the year, periods of the year were considered in the analysis. Most of the buildings were exposed to the sun for almost half of the day, actually in spring and summer, but the period decreased in fall, and especially in winter, of course. The insolation time also is observed that the insolation time is also affected by the location. The corner points of the buildings, actually, the interior parts of the corner points of the buildings are generally in shade and therefore very little exposed to the sun. So as a result of this analysis, solar energy has a good initial potential in the district, in the area, especially during the spring and summer seasons for the PET development, energy generation pillar of the PET development. But further information such as number and type of panels should also be considered, of course, to calculate precisely the energy potential, solar energy generation potential. And local authorities, companies, and other relevant stakeholders also, they need to be considered in the process to co-plan, co-design, and complement such as challenging projects with the lessons learned from the international projects as well to develop a positive energy district in the area. So I think that's it from my side. Thank you so much. Any questions will be, I think, considered at the end of the session.
So we are in time regarding the presentations. So we are even in advance of 5 minutes. The third presentation will be presented to you by Fairouz Zobiri from Centrica company. It concerns the local RES project.
Yes.
The floor is yours, Fairouz.
Thank you. So, good morning, everyone. Today I will present work that we have done in the scope of a local RES project. So maybe I can tell more about the local RES project. So local RES is about empowering local renewable energy communities for the decarbonization of energy systems. And so it takes this concept of energy community. So what is an energy community? And if you've seen some of the workshops this morning, you will see how hard it was to define an energy community. But so an energy community, we define it as a group of users that are located in the same geographical area, even though what that means is also quite open to interpretation. So they sometimes have renewable generation assets, they have energy storage assets, they have controllable devices, and so they can reschedule their consumptions to maximize the consumption of the locally generated electricity. And so in this talk, I will explain a little bit how what is behind those model predictive control that some of my predecessors have presented, and what is how the devices are actually optimized to maximize the local consumption of electricity. And so a little bit about the project itself. So the project will be presented in depth tomorrow at 2 o'clock in the Energy Communities workshop. But so this is just one particular work that was done within the project. But so the project consortium is quite large. We are 21 partners spread over 8 countries with 4 demo cases. And the project will run from 2021 to 2026, so it's quite a long timeline. And so the idea of the project is to bring together those energy communities with and to be able to test this control strategy. So why are we interested in organizing people in renewable energy communities, or RECs? Well, first of all, because as some of the workshops this morning have presented, people are mainly interested, or some people are interested in saving on their energy bills, but by consuming free locally produced electricity. And sometimes you may not have those assets yourself, so why not share the assets that your neighbors own? And some of the members of the community, and most of them, are motivated by environmental concerns, so consuming local electricity and green electricity. Also, some of the users are concerned about consuming from the local producers rather than large power plants that are located very far away with large electrical distances between generators and consumers, and so a lot of losses in these processes. And one of the last goals is to be able to provide services for the grid, because renewable energy often is pointed out as being intermittent, causing problems in the grid, being hard to predict. And so we can also show that it can help the grid by having this this flexibility that traditional assets do not possess. So how do we manage this renewable energy community? We use a concept called the MEVPP, which stands for Multi-Energy Virtual Power Plant. So the assets are organized in this platform, which has multiple inputs. So some of the inputs may be storage devices, battery capacities and parameters. It can be EV charging preferences. It can be heat pump settings, temperature control settings, and it can be a PV production, but there are also a lot more assets that can be included. Some of them were presented this morning, so that's quite nice to see. And the outputs would be, so that this virtual power plant would have as output the self-consumption schedule for the members of the renewable energy community. It can have extra services. There could be some peer-to-peer trading among the users. Some of the flexibility could be reserved for blackout strategies in case there are emergency situations within the local grid. We also reserve some of that flexibility to offer services to grid operators, and in this case it's mainly distribution system operators, where we offer congestion management, but it can also be transmission system operators with frequency services. So how do we manage these assets? So if we go back to our energy community, which is located in one geographical area with some grid in between. So these users, the prosumers within this community, can have a variable number of assets. They can have any subsets of the assets that we mentioned before, or they can have no assets at all and just be interested in sharing energy within their community. There could also be community-owned assets, batteries, and PV panels may be co-owned by the members of the community. And so the idea of our MEVPP is first to give priority to your own assets. So if you own PV panels, if you own batteries, we want to maximize or optimize the use of energy that you generated yourself. So you're the first layer of this MEVPP and you're given absolute priority. The second layer then would be the community. So if you have leftover PV, or if you don't have enough, then the next layer would be to trade with your neighbors or to share with your neighbors. So you would offer some extra PV generation to your neighbors, or offer some storage space in your battery or in your thermal devices. And finally, the final stage is If there is not enough energy within the community or too much, then the final stage would be to trade with the grid, but this is treated as a last resort, and the community is encouraged to be self-sufficient most of the time. So a little bit of mathematical formulation of the self-consumption problem of the renewable energy community. So here we're trying to minimize the cost of trading with the grid, which comes in terms of day-ahead tariffs or feed-in tariffs. And so we want to minimize these interactions. And then we want to, we don't really want to minimize community trading, but this term is here just to signal to the MPC controller that we want to prioritize in-home self-consumption, and then community is given a small artificial cost so that the in-home optimization is prioritized. And then the last objective is to do some peak shaving. We don't want to have peaks of energy demand, especially in areas where there are capacity tariffs, where you're built on this peak power consumption. And so this optimization problem comes with some constraints. So of course we cannot charge or discharge the battery up to more than its capacity. We need to maintain thermal or temperature comfort levels for the users. We cannot have too cold or too hot homes. We need to charge electric vehicles by the time that the user needs them, but we have a certain ready-by time that we need to respect. And finally, we need to respect the power flow within the grid. We cannot buy or sell more electricity than we consume. So the second service is that the second part of the MEVPP is dedicated to, after the self-consumption, it's dedicated to offering flexibility services to the DSO. And so why do DSOs require flexibility services? So as we mentioned before, the rise of renewables has made their job a little bit harder because these renewables are hard to predict. And as you may know, the grid needs to be, supply and demand need to be balanced at all times within the grid. And so that's a little bit harder to predict when renewables come into play. So one solution would be to expand the grid. So there is enough capacity within the grid to accommodate these renewables, but that's a very costly operation, and it's not very sustainable. We cannot expand the grid every time there are more renewable assets coming to a certain geographical area. And so what do we need to do? What does the DSO need to do? It needs to use these assets. So for example, if there is at some point a lot of PV coming into the community, instead of selling it all to the grid, instead of outputting all this PV into the grid, maybe use the storage to counter this increase in energy generation. And so the idea here, how we do that, the idea here is to split the services of the energy community. So some of them would be reserved to their own self-consumption, and some of them would be reserved for DSO services. And so we imagined this market where a DSO would acquire flexibility from the users, and these markets are still lacking in Europe, but in places like the UK, they're appearing more and more. So how do we include that in our optimization problem? So we solve a multi-objective trade-in problem where one part would be minimizing the self-consumption or minimizing the cost of trading with the grid, and the second part would be to maximize the revenue from the DSO, and for this we used the current imbalance prices that are available in some places in Europe, such as Belgium or the Netherlands. And so we still have these device constraints that we had before that we need to respect. And then we also imagine the case where these energy communities would have different managers, different aggregators, different suppliers. So in Europe, people are free to choose their suppliers, their aggregators, etc. So there could be many companies, many entities operating within the same community, and they're not always eager to share data with their competitors. So we imagined that we could, so we imagined the scenario, and we decided that all the optimization problems should be solved in a distributed way. So each aggregator will solve their own optimization problem, and then a consensus approach is used to iteratively try to reach consensus within the community. And so I can explain maybe a little more about how this flows within a day. So to be able to do these optimizations, we need to forecast how much PV we will have and how much demand there will be in the community. So we use some forecasting algorithms to forecast PV demand, but also hot water consumption. We use weather data, etc., to predict how much heating we will need, etc. And so once we have this 24-hour ahead forecast, we use the day-ahead prices in a distributed optimization. So the distributed optimization will optimize will solve the optimization problems that I've described before. And then, so it will give us the expected schedules for the next 24 hours within the community. But then we only apply the next hour. So we use a model predictive control approach where we only apply controls for the next hour, and then we repeat the process. We get forecasts that are closer to real time so that they are more precise, and we can repeat the optimization process. So as we go by, we have more and more accurate results. And so, sorry, here I can show some of the results that we obtained. And so, since we are using forecasts in our approach, and since the imbalance prices that are currently quite high, the optimizer tends to give a lot of portion of the community resources to flexibility services. And that's quite risky because these flexibility services can be binding towards the DSO, but it's not always possible to give them because we have forecasts that are uncertain. So we decided to have this virtual boundary between self-consumption and flexibility, and to test some restrictions on these flexibility services to see how we can balance cost with uncertainty of forecast. So, for example, here, if we don't have any flexibility, the costs within the community were quite high, and we use this prices. So this was a week in summer, quite a lot of PV, and then so the more we add flexibility, the more we reduce the total cost. So because the total cost is self-consumption minus rewards, so the more we add. So as we can see, the cost of buying from the grid doesn't increase that much, but the total cost decreases drastically. So if we are able to get very precise forecasts, it would be great, because we would have we would eliminate the cost of running the community. Yeah, that was it. So as a final word, I can maybe say a little bit about the demo sites where we will test the multi-energy virtual power plant. So we have 4 demo sites. 2 of them are in Italy, so in the community of Osimo, but also in Berchida, which was presented in some of the workshops this morning, and that's in Sardinia. It's a quite mountainous region, and so there is a lot of PV potential in these 2 communities. Then the other 2 communities are in East Pasteur in Spain, and then in Austria, and each of them tests different aspects. So for example, in East Pasteur we have a lot of storage, so we can test how storage, how by adding storage we can maximize these services, while all the store focuses on other services such as flexibility, peer-to-peer, and blackout strategies. So that was it for me, and please let me know at the end of the session if you have any questions. Thank you. Thank you all.
So you can see well coherence between the projects presented. So firstly, the ADSorB project presented us the storage technologies. Secondly, Propel project presented us the concept of the positive energy districts. Last presentation from Centrica was focused on the energy communities. And my presentation will be focused on the smartness of buildings and how to improve the smartness of buildings in order to be able to absorb all these technologies you have just presented. So I am Perevozchikov Igor from R2M Solution company. I am smart building engineer, and I am also a temporary teacher of building management systems in a high school, ENS Tueday, in the south of France. Probably you know already R2M Solution company. It's also only some words about. It's a consulting company in the domains of energy, sustainability, smartness of buildings, and smart grids. And this is also one of the companies who is organizing this Sustainable Places conference. So, EVELIXIA project and how to level up the SRI class of building. The problems is the next one. You can see it here on this picture. We can, nowadays, we can evaluate the smartness of buildings, what are the smart technology presented into the buildings, what are the automation functions installed into buildings in order to optimize its energy use and its user. But we don't know how to improve it. The evaluation of smartness of buildings, it's a punctual operation. We evaluate it's called the SRI Smart Readiness Indicator score at one time. We have a SRI score, we have SRI class, but the stakeholders, so the building managers, building owners, don't know what they should do with it, how to go to another SRI class, how to raise the SRI score in order to have more of comfort for occupants of buildings, in order to optimize the use of buildings from energy efficiency point of view, and in order also to answer on the growing demand about flexibility services for buildings, how to, what they should do in order to go to improve the buildings in that three functionalities. So it's one of the goals, it's our work of R2M Solution in EVELIXIA project, which is the Horizon 2020 project, innovation action, which started from 1 year ago about, and has a duration of 4 years. It's a quite big project with 36 partners in totally from 12 European countries and 7 pilot sites. And so the partners, you know some partners from this project. This project is coordinated by CERT from Greece. The goal of the project is, the main goal is to realize buildings as active utility nodes. What it means? It means that the idea of the project is to create like a platform who will join different kind of stakeholders who were working before independently. So from one side we have building and facility owners and users. They have been managed as a building in order to have more comfort, to pay less for the building use. From another side, we have system operators, DSO, TSO, etc. The main goal for them it was to operate the energy grid efficiently in order to avoid congestion and to balance demand and supply. And the third kind of stakeholders, these are the energy market stakeholders, which are the aggregator, which are energy suppliers, who were working also in some interaction with system operators, and with users also, consumers, but also not really integrated into this ecosystem. And so the idea of the project is to create an EVELIXIA platform who will provide several services, so building to grid services, grid to building services, human to building interfaces, system interoperability services, and flexibility enablers to all these kinds of stakeholders I listed, I mentioned it just before, in order to integrate buildings as part of the common ecosystem, so as active utility node. In this way, the bound framework we are developing in the EVELIXIA project incorporates mainly through three things. So the first one, we need to integrate and coordinate the building infrastructure with IoT energy management system and with grid. This is done by building to grid and grid to building services, and also by the concept of autonomous building digital twin and autonomous district digital twin. I mean here that there are some services who are as part of the building digital twin, and also some services which are a part of district digital twin concept. Secondly, we are developing a services marketplace in order to give the possibility to stakeholders to construct, access, and exploit novel services and business and relevant business models. And thirdly, so we need to engage the stakeholders to interact with them from a visual point of view. So we need like a graphic user interaction platform, and we also from social point of view. So we have a concept of EVELIXIA stakeholders interaction platform, which englobes a live digital building logbook and visual analytics engine. And this framework is also based, we are considering the privacy and security, and so this is based on the blockchain infrastructure in order to provide this privacy security to all these stakeholders. The pilot sites of the project, there are 7 pilot sites which have been chosen accordingly to different kinds of buildings. So we have apartments, residential, we have non-residential buildings, restaurants, hospitals, industrial buildings, and accordingly to different climates. So we have a climate more oceanic, like a French climate, like Spain, Denmark, and we have a Central Europe climate also. And we have a Greek demo site who is a part of South Europe climate. This is the overview of the architecture, of the technical architecture of the project, which is structured in 3 layers: field layers, data management layer, and application and services layer. Field layer we have here, so the BIM models, which is constructed, the data points from meters, from sensors, from IoT devices. Data management layer, it's like an intermediary layer who is providing us the interoperability between this kind of points. And it's like a broker also between services layer and the field layer. The blockchain infrastructure is also considered in this data management layer. And the third one, so this the highest level, it's the services level. Here, where we have all the services which are hosted. So autonomous building digital twin framework, englobing some services for decision support and forecasting at the building level, and autonomous district decision digital twin, englobes the services for district decision support system and forecasting system at the scale of district. And we have also a tool which is named SRI Advisor Tool, which is finally the main scope of my presentation. We are developing this tool in order to provide building owners and managers with tailored recommendations of about how to level up the SRI class by 1 liter. This is the first goal of the tool. This tool analyzes several scenarios in order to determine the most cost-effective building upgrades in order to achieve a higher SRI score, and finally give some answer on the questions of building owners and managers about what are the measures they need to do in order to improve the smartness of their buildings. And so R2M is developing this tool together with CERT. And the third aim of this tool also is to give the tailored recommendations. So the SRI Advisor tool should consider each building it's applied in order to give the recommendations which are adapted to building. For example, for this building, with such number of windows, with such numbers of rooms, with such number of floors, located in Luxembourg. So we take into consideration also the location of the building in order to give tailored recommendation and to simulate in a precise way the most cost-effective building upgrades. Just some words about the Smart Readiness Indicator. So it's a European framework which has been developed, introduced into the EPBD directive in 2018. So he was going through the updates of this directive up to the recent updates in 2024. And so before the different live projects, you have seen it in other presentations, and the assessment platforms which have been developed. It was as an Excel file with 54 services listed, covering 9 technical domains, so heating, cooling, ventilation, domestic hot water, electricity recharge infrastructure, monitoring and control, lighting, and dynamic building envelope. And so each assessor should select the corresponding level of functionality for each of services. So now with different live projects, live program projects, there are several SRI assessment and calculation tools which have been developed. And for the SRI Advisor tool, we are using the results of SRI assessments done as inputs for SRI Advisor tool in order to run optimization engine. And so the objective, the function of optimization engine is to maximize the net present value of possible renovation packages. And so what we are considering as inputs also for this optimization engine, this are the CapEx costs which are associated to the functionality levels of each of SRI services. So firstly, we need to identify products, technology products like sensors, like different kinds of automation systems associated to each of level. The OPEX costs, which are the maintenance cost by year for each of these products and systems. The benefits from the upgrade from one functionality level to another. And finally, the initial SRI score, we need to take it into the consideration. We have some challenges. So as you can see, the CapEx cost depends on from a country. The cost of products not the same in Luxembourg and in Bulgaria. The CapEx cost depend also from the different possible technological choices. Sometimes we can implement the same functionality level by systems from produced in France and in other countries. And it's very in time also. The cost of products now, it's not the same cost like 4 years ago. For OPEX cost, we have the same challenges. As for the CapEx, for the SRI score, we are using the SRI assessment tool results as inputs also. And for benefits, which is most complicated and it's also multidimensional, this is a big challenge of this tool, how to evaluate the convenience benefits or the benefits to the comfort of occupants from changing, from going to the increased convenience of motorizing blinds. So it's a question we don't have a response up to now. We can evaluate energy savings from some kinds of building upgrade measures. If we concern the heating, ventilation, and air conditioning systems, but how much energy may be saved if blinds are motorized? So it's also a very complicated question to be answered, to be evaluated, and after we need to monetize the savings by country, depending from country, from electricity tariffs, etc. So this is a bigger challenge. The SRI Advisor tool architecture, you can see it here. 4 inputs, SRI assessment baseline data, characteristics of the buildings. We need to know what is the number of windows. We need to know what are the energy systems which are installed, what sensors are installed into the building and what meters. A renovation measures cost. It's something we started to construct this database with products associated with the costs of products associated to each building upgrade. and manpower cost also, and user preferences. User preferences for some building managers, it could be more important to have building upgrades to optimize energy efficiency. For some and other ones, it could be more important to optimize the comfort of occupants. So we need to take it into account. And the outputs of the two, this is a proposition of building upgrades with a change of class from one class, SRI class, from one to another, with CapEx cost, OpEx cost, and impacts criteria, how it impacts the building. We have developed a graphic user interfaces which supports this SRI advisor tool. The cost database, it's something I already said we are progressing now, and it's not an easy task because we have introduced also a correction coefficient for country in order to take account the manpower cost between differences between the countries and the unit costs difference also. And the user output interface is done here. So as I said before, SRI score improvement with SRI class improvement and with associated costs. To conclude here, so at the beginning of the project, it was one of the first, I can say even, it was an innovative tool which have not existing in another projects. Now there are another project like SRI Enact, EasySRI, which consider this kind of tools and which go also in this direction. This is also the request from building stakeholders, so it's a real need from them because they don't know, and in order to promote the SRI, we need to advise them about what are the building upgrades they can implement. And as I said, we have encountered some problems about the quantification and monetization of energy savings and benefits on comfort, on maintenance, on other impact criteria, which is also depending on from country and electricity tariffs. And the risk we have identified is the reliability of cost data. So we are developing the cost data now in 2024, but in probably 2 years, it could be not the same cost. So we need to take it into consideration, and we need to use also the online database with a dynamic cost associated to this product. Sometimes it exists, sometimes not. So thank you very much for your attention. We have finished the presentations slot. It's now time to questions from public. Yes.
We did a study, not an EU project, but that was for a local a group of municipalities, which includes Antibes and Cannes and this area in the south of France. And in fact, we adopted a similar approach, but in addition to the solar potential, we had many, many layers, and some of them, in fact, related to regulation, for instance, for instance, how close the building is to the sea, because it has an impact potentially on solar panels. And there was also all the aspects regarding the complexity of the roof and its potential to host solar panels. So in fact, we had like 10 layers of extra complexity on top of just the solar potential of the surface. So wanted to know if you consider that as well in your project.
It was the professor, as I mentioned, but I think they just considered two types of roofs, terraced and pitched roofs, in the analysis. But I'm sure that there should be more archetypes, as you mentioned. Yeah. I also have a question, maybe I can.
Yes, please.
To Robert first. Robert, yeah, since you're a native speaker, your presentation was perfect, and maybe I couldn't catch it. That's why I'm re-asking it. Okay. So sorry for the inconvenience. So what is the output temperature of the PSM that you connected with the heat pump? And it's an air-to-air heat pump, I think. And what is the COP of the heat pump for the PSM?
Okay, so the phase change temperature of the material is 53 degrees. And so, yeah, so essentially it's 53 or slightly lower, because obviously you put in some cold water through the heat exchanger within the PCM store. That's cold. It could be 10-degree water if it's coming from the mains, or it could be slightly higher if it's coming from elsewhere in the system. So obviously that drops things down a little bit from 53 degrees, but it's in that sort of ballpark. And obviously the slower you run the flow rate through the unit, the closer you get to 53 degrees. So obviously it depends what you're running, and we're learning from the installed units as to what their COP is. Over the summer we've been getting 3+ without any great challenges. The real challenge will be coming through this winter when we see what happens when the external temperature drops. And obviously it's also a function of what we're asking the heat pump to do. So if essentially what we're doing at the moment is tricking the heat pump into providing domestic hot water level heat coming out in order to charge the PCM stores. So we're essentially asking it to give it our maximum. The heat pump we've chosen, it's an air-to-water heat pump, so it's a hydronic system. It will provide 65 up to 70 degrees, depending on the external conditions. But obviously at those levels, the COP starts dropping from the ideal. It's much higher if we're asking it to produce 40 or 50 degrees. It's just a standard Dakin unit, modern heat pump. It's not propane refrigerant, which would give it even better, but it's, yeah.
And lastly, do you consider PSM as a seasonal storage?
So we wouldn't. Yes. So PCM, essentially we've captured the round trip efficiencies, and if you charge the unit to full and left it in 20 degrees, it would discharge itself over the course of a week or so. And of course, as time goes on, you start getting less and less usable energy coming out. So it's really within the day it's ideal for. Over 2 or 3 days, it works pretty well. The thermochemical storage could be interseasonal if you chose to. I don't think there's going to be a lot of interseasonal storage using thermal storage technologies. I think if people are wanting to do interseasonal things, they'll be looking at hydrogen or things like this in the future, because that makes a lot more sense for really long durations. But there isn't enough focus, I don't think, on those medium durations, depending on how you characterise those. Thermal storage could be a possibility there. Something between lithium-ion that's very fast and hydrogen that's very long duration. There's a middle ground that needs grabbing. Thermal storage could be the key to that, I think.
Because we had PCM implementation in one of our projects, but
okay.
At the end they couldn't do it, that's why.
Okay.
Because there we identified it as a seasonal storage.
Right, okay.
But you think it's not so...
Obviously it depends on what medium you're using and the phase change temperatures and so on, but for us...
Like salt or salt-based.
Oh, okay, right, yeah, so that could be for long durations. Great.
I have also a question to you, Robert. So what is the efficiency of phase change material and thermochemical storage? And the second question, if there is during a cold night, there is a -5 outside, what is the size of thermal storage system adapted for one house in order to be able to adjust the efficiency of the heat pump and to cover the whole night? Because the systems, mainly the thermochemical storage you have presented, there is some sizes associated, and I'm curious about it.
Yes. So I'll do the first question because that's got less uncertainty associated with it. So we've, for the PCM stores that we've got, so we've done the characterizations, and the curve starts. If you immediately charge the unit and discharge it, the round trip efficiency is somewhere in the high 80s or thereabouts. So that's reasonable. You can think of it as a sort of 7 or 8% loss on charging and discharging. The crucial thing is that round trip efficiency is fairly well maintained for within the day. You only lose a small amount over the course of the day because they are essentially kind of self-insulating. They don't lose a lot of heat because you're storing things at a lower temperature than you might choose to do in a sensible heat store like a hot water tank. So you get fairly low losses over the course of a day or two that might be operating over. And like I say, after 6 or 7 days, the thing is empty, but you wouldn't tend to operate things that way. So that's the easy question. We'll be publishing those results in time. The second one is a much more complex and nuanced question because it's so dependent on what that house is doing, how well insulated it is, whether this is a nice new build property that's built to passive house standards, or whether this is what we see in the UK, which is a leaky 100-year-old house that's had some bit of insulation done to it. So it's such a function of the heating loads within the building and what's going to be required that it's very hard to say how large or small something might be. What I would say is we see typical space heating loads that can vary between, on the coldest days, it tends to be in the sort of low tens of kilowatt hours heating that you might need for a 24-hour period. Obviously through a night, that's only a portion of that period. And so when we're talking there about a TCS store with a 50 kilowatt hour heat capacity, that could, you would hope, certainly look after a day's worth of heating in any sort of sensible location. But there's so many different ways of configuring the systems, and it starts then coming towards the kind of optimization tools you're looking at in how you set out these systems, what's the appropriate scale in order to serve a home, or does it make sense for putting these kind of stores on a district heat network, for example, or a community heating network, and that being where you're doing the bulk of your storage, such that you can serve multiple properties rather than have one large unit outside a single home. Okay. That goes some way to trying to answer a very uncertain.
Okay, so from with about 4 PCM modules, you can cover, if I can say it, a building, a small house with the energy required during a cold night, for example.
Yes, you would hope so. What I would say is that evenings don't tend to be the big challenge from a grid perspective because, okay, cold nights, people turn their heating on, but usually to a lower level than they might want to do in an evening. So it's that sort of 5 to 10 p.m. that's the big challenge for covering, and that's when there's also tends to be still existing demand from other sources, from industry, from other things. So the nights are a challenge, but not typically the biggest challenge. It's the peak periods we want to cover. Is it okay if I ask you a question in response?
Yeah, it's okay. Thank you.
So, we come at things from an optimization perspective, as you do. You mentioned the challenge in getting costings for CapEx, for OpEx, for quantifying benefits, and so on. And you mentioned the challenge of estimating capital costs in particular, that might rise over a 2 or 3 year horizon quite substantially. I'd suggest that the bigger challenge is quantifying the benefits of a solution that might be going in and operating for 20 or 25 years, because the uncertainty gets compounded over such a long period of time. Have you put very much thought into how to account for that uncertainty within your optimization approaches?
So finally, about the calculation of benefits, for the moment we have selected to be focused mainly on the costs associated to each of functionality levels. So to the CapEx and OpEx costs and to the manpower costs associated to it. And the second point, the second variable who is entering into this optimization, it's the SRI score improvement. So we consider the cost, SRI score improvement, and without taking into consideration the benefits associated for that time. Another project, like I think EasySRI, has considered only partially energy savings associated to only some services. But this is not our approach, because if we consider, we don't to do a simulation based only for some SRI services. If we do the evaluation of energy savings benefits, we need to do it for all the 54 SRI services and all the levels associated to it. So it's we need of resources, of time to do it. And so in the framework of this project, we don't plan to do it.
Time is always the biggest constraint.
Yeah.
So my question is also to you, Robert. So you mentioned that you had developed a new way of evaluating the SOC of the thermal storages. Could you say a little more about that, if that's possible?
So this is very much work that's under development, so the papers are to follow. But we've looked at a variety of approaches at different levels of complexity for how we do that for the phase change material stores. We're fortunate we've obviously got the lab set up, so we've got temperature sensors on there, the baseline level of observability, if you like, some internally, but some outside the unit. And we've found that we can learn some useful things about where we are in the self-discharge process, if you like, when you leave the stores to in their idle state, by observing those temperature measurements that aren't in the active material, but are a small step away from it. There's still some informative data there. They're not very sensitive, but there's enough to go on. Other approaches, there are some fairly simplistic things where we can just learn from those kind of round-trip efficiency calculations what we'd expect to have left in the store if we've left it for X amount of hours in Y temperature conditions. So we can kind of build up some standing loss relationships that we can then make use of. We're pushing a little bit more into more complicated kind of state space models of the system to characterize things a bit better. But we are also looking at different sensor modalities. So what we can do beyond temperature sensing. There's all sorts of different things that you can play with to try and learn about what's happening within the storage devices themselves. So that's probably lower TRL, but potentially another useful way of getting more observability of what's happening in there.
Yes, of course.
I think this multi-energy virtual power plant is a very interesting concept. In one of the first of the slides, you show that some owners can have residents can have storage, some can have PV, whatever, or charging stations, batteries, and some can have heat pumps that can be shared with the others. So, is the heat pump used as building scale heat pumps or district scale heat pumps?
Thanks. So for the heat pumps, the heat pumps that we have so far are just individual, but we think that there could be some district heat pumps. Not sure about buildings, because most of the locations that we have are rather smaller towns with individual homes most of the case, so not a lot of buildings in there. We have some buildings, but they're mostly municipal buildings, and we didn't see any heat pumps in there. So if there would be heat pumps installed, it would be district heat pumps so far.
And again, the multi-energy virtual power plant, who owns it? Because you have started as a Horizon project, it's a local res. Of course, there's a big consortium running for the project. So, do you think this is really replicable in other energy communities? Who will? I'm asking this in terms of capacities. Who will run the virtual power plants?
Yes.
The community itself.
Yeah. So that's an interesting question, because the legislation can be quite different in different countries. So, for example, in most the cases that we have seen, the energy community is a legal entity by itself, and so there is in Austria, yeah, especially in Austria. So there are many layers. So there is like a legal entity that owns the energy community, and that's they are. Yeah, it could be like a cooperative or and in some cases, so the legal entity can also be many stakeholders. So in some cases, for example, in Italy, the municipality is quite involved. I'm not sure about the legal status of how if the municipality can have some stakeholder relationship with the renewable energy community, but that's not necessarily the case. But in all of these cases, municipalities were quite involved. And then, so especially for, yeah, I would recommend taking a look at the Austrian pilot, because that's a very advanced renewable energy community that has been up and running for many years, and so they are their own legal entity, which owns and runs the resources. And so, yeah, one of the challenges also there was to be able to access the assets, because yeah, and in most in that case, what we can do is have access to an aggregate sort of measure of the flexibility, an aggregated measure of the flexibility that we can later offer in various markets, but not control over individual assets, which would be done later by the owner of the renewable energy community. Yeah, yeah, it's depending on the location, yes. The regulation in place and the so the relationship between and this case was also particular because a lot of these renewable energy communities are involved in different projects, so it could be quite tricky to take away, if you want, the assets from their other use. Yes, yeah, exactly. Yeah, exactly. So, so yeah, that's a very interesting question. It's yeah, it depends on legislation in every country, but yeah, that's something that that needs to be taken into account. Yeah.
Thank you. I have probably one last question to one of you. Probably firstly to Beril. Have you accessed the potential also wind turbines probably for positive energy districts, or it was only solar potential which has been accessed? And the second question about the social acceptance. Do you consider it, to both of you, in positive energy districts and in energy communities, do you consider the social part of social acceptance by final users, by occupants, or not?
In the research, it was just focused on the solar energy generation. That's why the energy consumption, the final energy consumption of the buildings are not calculated, considered yet. Also the demand and yeah, so the energy delivered is not calculated yet. So that's why I don't know if it really covers, it really meets the generation really meets the consumption for now. But it will be conducted in the next stages of the project. And in terms of social acceptance, it's actually one of the questions I think I also asked her to present, because it really depends on the context of the district, you know, social context, and also not just social, of course, legal context, and also other economic contexts of the geography. And if the social acceptance is not there, of course, you can never ever conduct, manage, develop positive energy districts in the area. This social technological transformation, so you cannot do it without any social acceptance, in my opinion.
Thank you.
If I can add something about the social acceptance, so it also depends on how invasive the technology is, because most of the time when, so for example, when we access aggregate resources that do not need extra installations in people's homes, that's better than when you need to install sensors, controllers, etc. into people's homes, so that the invasiveness of the technology is definitely something to consider, especially when we are a technology provider. So we, in most cases, like to have control, full control of the devices, but maybe we need to rethink how to work with the users instead of work despite their being there. So that's also, yeah, that's challenge for putting in place this technology.
Yeah, as everything which is innovative, it's also challenging to put it into the grand public. So thank you very much for this paper session. It was a very interesting session. If you have questions to some of us, you can write it, pass it to me, or write through the B2Match platform. And so see you later. Thank you very much.